They don't shine like ordinary stars, nor do they have swirling gas clouds like planets or nebulae. Neutron stars are compact, dense, and dark more shadow than light. Yet, remarkably, we've uncovered a wealth of knowledge about them. We've studied their pulses, traced their magnetic fields, and even detected the ripples they send through space-time. But how do we study something that's nearly invisible? The answer lies in the subtle traces neutron stars leave behind. Despite being small and visually faint, they communicate through other cosmic channels: radio waves, X-rays, gamma rays, and even gravitational waves. With the right tools and enough patience, we can intercept these signals and piece together their stories. Let's begin with the most well-known method: radio telescopes. This is how neutron stars were first identified in the 1960s. Large radio dishes scanning the sky picked up a repeating signal, steady and rhythmic like a clock ticking in the dark. That signal turned out to be a pulsar, a neutron star emitting beams of radio waves from its magnetic poles. As these beams sweep past Earth, we detect them as regular pulses because neutron stars spin so consistently. Their radio pulses can be timed with extraordinary accuracy. By tracking when these pulses arrive, scientists can measure a star's rotation rate, how quickly it's slowing down, and whether it's orbiting another body. Tiny irregularities in timing can even reveal internal changes or nearby gravitational influences. Radio observations also allow scientists to map the structure of the magnetosphere, the magnetic bubble surrounding the star. Variations in pulse shape and brightness offer clues about particle movement and magnetic conditions around the star's surface, but not all neutron stars emit strong radio signals. Some remain quiet in the radio band but blaze brightly in X-rays and gamma rays. Observing these higher energy emissions requires space-based telescopes, such as NASA's Chandra X-ray Observatory and ESA's XM Newton. These instruments operate beyond Earth's atmosphere, which blocks most high-energy light from reaching the ground. From orbit, they observe neutron stars emitting bursts, flares, and steady X-ray streams. Many such emissions come from neutron stars drawing in matter from a nearby companion. As this material falls inward, it heats up, sometimes reaching millions of degrees, and emits X-rays. In binary systems, this process can lead to dramatic flickering, spinning, and sudden flares as matter collides with the star's surface. X-ray telescopes are also crucial in studying magnetars, highly magnetic neutron stars that sometimes erupt with bursts of energy. When a magnetar flares, it releases intense streams of radiation. X-ray observatories are often the first to catch these outbursts. By analyzing brightness patterns over time, researchers can learn about internal processes like glitches, flares, or magnetic stress relief. Then there are gamma rays, the most energetic form of light. Some pulsars, especially younger or more energetic ones, emit gamma rays from their magnetic poles. These photons are rare and difficult to detect, but incredibly informative. Specialized instruments like the Fermi Gamma Ray Space Telescope help us understand how particles are accelerated in these extreme environments. In recent years, a revolutionary tool has joined our observational arsenal, one that doesn't rely on light at all. This is gravitational wave astronomy. Predicted by Einstein over a century ago, gravitational waves are ripples in spacetime caused by the motion of massive objects. They were first directly observed in 2015 when two black holes merged and sent a ripple across the cosmos. In 2017, scientists detected another gravitational wave event, this time from two neutron stars merging. This collision, called GW170817, was a watershed moment. Not only did it produce gravitational waves, but it also emitted light across the spectrum: X-rays, gamma rays, visible light, all observed by telescopes worldwide. It was the first time a cosmic event had been detected both through gravitational waves and light, giving us a much fuller picture of what occurred from this single event. We confirmed that neutron star collisions generate kilonovae, brilliant explosions that forge heavy elements like gold and platinum. We also saw that these mergers can produce black holes, gamma ray bursts, and major disturbances in spacetime itself. More recently, Astronomers have begun studying fast radio bursts, FRBs, brief intense pulses of radio waves from distant galaxies. While the origin of FRBs remains unclear, one repeating burst has been linked to a known magnetar, strongly suggesting that some FRBs originate from neutron stars, undergoing magnetic outbursts. There's also growing interest in neutrinos, tiny, nearly massless particles that can pass through almost anything. Neutron stars produce vast numbers of neutrinos during their formation in supernova. Although difficult to detect, future observatories may be able to observe these elusive particles more often, offering a deeper look into the violent births of neutron stars. It's worth reflecting on just how remarkable this is. From a small planet orbiting an average star in a quiet corner of one galaxy, we've developed instruments that let us study the remains of stars thousands or millions of light years away. We can't touch neutron stars. We can't visit them or collect samples, but we can listen, we can observe. We can detect their pulses, flares, and gravitational echoes. We've come a long way from the days of telescopes and glass lenses. Now, we have a symphony of instruments: radio, X-ray, gamma ray, gravitational wave, and neutrino detectors working together to tell the stories of these distant remnants. Neutron stars hide in darkness, whisper through the cosmos, and leave only subtle traces behind. But with careful listening, we find they've been speaking all along in radio flashes, bursts of light and ripples in space itself, and perhaps the most astonishing part? We've only just begun to listen. Countless signals are still out there, drifting through space, waiting to be discovered. Neutron stars spend most of their lives alone, spinning in silence and emitting steady pulses. But occasionally they find a companion other neutron star or a massive star not yet collapsed. When these bodies orbit close enough, an extraordinary sequence unfolds over millions or even billions of years. Their orbits tighten, the pace quickens, and eventually the two objects merge. When they do, the result is one of the most extreme events in the universe, a kilonova. Let's break it down. Imagine two neutron stars locked in orbit. They may have originated as a binary star system, two massive stars that each went supernova, leaving behind neutron stars. If their gravitational bond survives, they'll continue orbiting their shared center of mass, slowly spiraling inward. This inward spiral is driven by the emission of gravitational waves. Each orbit sends a small pulse of energy into spacetime, slowly draining the system's momentum. Over immense timescales, this loss of energy brings the stars closer. As they near each other, their orbit accelerates. Years become months. Months become days until they're circling each other many times per second. And then they collide. The merger releases an extraordinary burst of energy: gamma rays, gravitational waves, and a brilliant radioactive explosion, a kilonova. These are a unique kind of stellar event, less luminous than a core collapse supernova, but far more powerful than a typical nova. They shine about 1,000 times brighter than regular novas, hence the prefix kilo. But the most fascinating aspect of kilonovae isn't their brightness, it's their role as cosmic forges. They're one of the few places in the universe capable of producing heavy elements like gold, platinum, and uranium. These elements can't be formed in normal stars. Fusion inside stars only creates elements up to iron. Anything heavier needs extreme environments, dense with neutrons and driven by rapid processes. That's exactly what happens in a neutron star merger. Chunks of neutron-rich matter are ejected into space. As this matter cools, it undergoes rapid neutron capture, what scientists call our process. Nucleosynthesis. Atomic nuclei quickly absorb neutrons and build up into heavier elements in just seconds. When the dust settles, what's left is a cloud of newly forged elements drifting through the galaxy. Eventually, these particles become part of new stars, planets, and even people. That gold ring on your finger, the platinum in your devices? They might have originated in the collision of two neutron stars billions of years ago. We've long suspected this, but in 2017, we finally had proof. Gravitational wave detectors picked up GEO-170817, a ripple caused by a neutron star merger, 130 million light-years away. Seconds later, Gamma rays were detected, and telescopes worldwide scanned the sky for the source. They found a faint glow, a kilonova. Over the following days, its light shifted in brightness and color. Spectra revealed the presence of heavy elements. It was definitive proof. Neutron star collisions create gold, platinum, and other R-process elements. This event marked a turning point in astronomy. It was the first time we observed a cosmic event. Using multiple types of signals, gravitational waves, light, X-rays, and radio. This approach, called multi-messenger astronomy, allows us to form a more complete picture of the universe. From GW 170817, we learned that neutron star mergers are more than just cosmic fireworks. They're essential to the chemical evolution of the universe, the source of many of the elements that make up planets, life, and technology, but not all kilonovae come from neutron star pairs. Sometimes a neutron star merges with a black hole. These events vary widely. If the black hole is too large, it may swallow the neutron star completely, with little electromagnetic display. But under the right conditions, it can tear the neutron star apart, creating a brief but brilliant kilonova. These mergers are harder to detect but equally valuable. They help astronomers understand the population of compact objects in the universe and the diverse ways they shape cosmic history. In binary systems, neutron star mergers reveal both the limits of stellar structure and the boundaries of physics. Each collision marks a new chapter in the story of star evolution, offering scientists a chance to test theories under extreme conditions. Some researchers suggest that when two neutron stars merge, they might briefly form a hypermassive neutron star. This object would be so dense and heavy that it could only exist for a fleeting moment before collapsing into a black hole. During that short lifespan, it might emit complex gravitational wave patterns, providing a rare window into matter under the most extreme pressure. Though brief, these signals leave long-lasting marks on the cosmos. Gravitational waves race outward at light speed, gamma rays streak through space, and the kilonova glows briefly before fading, scattering heavy elements across the galaxy. And here on Earth we detect it. We analyze it, we learn from it. These rare cosmic events offer a glimpse into the distant past, not just the history of stars, but our own. The iron in your blood, the iodine in your thyroid, the gold in your jewelry, all trace back to events like these. Neutron star mergers don't happen often. In a galaxy like ours, one might occur every 10,000 to 100,000 years. But when they do, they're brilliant, brief, and rich in information. They show that even in destruction, the universe creates that out of violence can come beauty in the form of glowing light, precious metals, and new elements. So next time you see gold or platinum or any rare element we prize on Earth, take a moment to remember, these didn't come from the soil, they came from stars. Not just any stars, but the densest stellar remnants, locked in a slow spiral that ended in a single, spectacular collision, a collision that shook space and time, lit up the universe, and maybe even helped create you. At this point, Neutron stars might seem like they've revealed all their secrets: crushing gravity, intense magnetism, time-warping spin, and explosive endings. But we've only just begun to understand them. At their core, neutron stars may contain some of the most exotic, least understood matter in the universe. This is where things get truly strange. You may know that neutron stars are made mostly of neutrons, the neutral particles found in atomic nuclei. But under the extreme pressures found deep inside, neutrons might themselves break apart into more fundamental components. Quarks. Let's step back. Quarks are the building blocks of protons and neutrons. A proton is made of two up quarks and one down quark. A neutron has one up quark and two down quarks. In normal conditions, quarks are always bound in these groups. They don't exist on their own. But at the crushing densities inside a neutron star, it's possible that neutrons break down, releasing quarks into a free-flowing state known as quark matter. This hypothetical form of matter is called quark-gluon plasma. Scientists believe it once filled the universe during the first microseconds after the Big Bang, an ultra-dense soup of quarks and gluons, the particles that bind them. As the universe cooled, these particles joined to form the protons and neutrons we're familiar with. But inside neutron stars, the conditions might be extreme enough to recreate that early chaos. At sufficient pressure, quarks could flow freely, forming a dense, frictionless fluid of up-down and possibly strange quarks. This form of matter is sometimes called strange quark matter. Why strange? Because it includes strange quarks, which are heavier and less common in everyday matter but may stabilize under high pressure. If stable, this matter might form the core of some neutron stars. Some physicists even think strange matter could be more stable than regular nuclear matter. If true, it could have dramatic consequences. One idea suggests that a single droplet of strange matter, strangelet, could convert nearby ordinary matter into more strange matter, like a kind of subatomic chain reaction. In theory, one strangelet could spread and transform entire stars or planets. While fascinating, there's no evidence that this has happened or ever will. There are other exotic possibilities. One is the hyperina particle similar to a neutron, but containing additional quarks, such as strange quarks. Hyperins are unstable under normal conditions, but deep in neutron stars, they might exist long enough to influence the star's structure. Why do these details matter? Because the material inside a neutron star determines how it behaves, how much mass it can support before collapsing into a black hole, how it responds to pressure, and how it emits energy. If the core is made only of neutrons, certain rules apply. If it's made of quark matter or hyperins, those rules change. It's like trying to predict how a cake bakes without knowing if it's made of flour or foam. Some scientists think that quark stars, entire stars, made of quark matter, might be a separate class of objects. These hypothetical stars would be smaller and denser than neutron stars, possibly forming when a neutron star compresses further but doesn't quite collapse into a black hole. If quark stars exist, they'd be among the most extreme objects in the universe. From a distance, a quark star might look very much like a neutron star, pulsing, spinning, emitting radiation. But small differences in how they cool or react during mergers could reveal their true identity. Future telescopes and gravitational wave observatories may be able to detect these subtle clues and confirm whether quark stars are real. And because the universe is full of surprises, there are even more speculative ideas. Some researchers propose that dark matter, the unseen mass that dominates the universe, could collect inside neutron stars over time. This might alter their structure or even cause collapse. Others suggest neutron stars might host exotic states of matter like Bose-Einstein condensates or pion condensates, rare forms of quantum matter we don't fully understand but may emerge under extreme conditions. In this way, neutron stars act as testing grounds for some of the most outlandish ideas in physics. They sit at the intersection of gravity, quantum mechanics, nuclear science, and particle physics, pushing each to its limits. What's exciting is that we're on the verge of learning more. Instruments like NICER aboard the International Space Station are measuring neutron stars with unprecedented precision, helping scientists narrow down their size and mass. These measurements inform the equation of state, the relationship between pressure and density inside the star, which in turn reveals what it's made of. At the same time, gravitational wave observatories like LIGO and Virgo are capturing neutron star mergers in action. The shape of the waves they emit encodes information about how neutron stars bend, stretch, and deform, clues about their internal makeup. All of this brings us closer to answering some of the most fundamental questions in science. What is the most stable form of matter? How does the universe behave under maximum compression? What's really inside a neutron star? Neutron stars don't just stretch our theories, they redefine them. They highlight the limits of our understanding and guide us toward the unknown. As we study them more closely, we might discover not only what neutron stars are made of, but what we are and what the universe still has in store, because strange matter, quark stars, and hyperin cores aren't just theoretical oddities. They're real possibilities, echoes from the edge of modern physics. Waiting for someone to listen carefully enough to understand them, neutron stars might appear to be cosmic loners born in the aftermath of stellar death, spinning in solitude, far from the luminous regions of space. But despite their isolation, they play an outsized role in our understanding of the universe. For one, neutron stars are natural laboratories. We can't recreate their gravity, density, or pressure in any lab on Earth, but they do it effortlessly. By observing them, we conduct experiments that no machine on Earth could replicate. They allow us to test physical laws under extreme conditions. Einstein's general theory of relativity, for example, has passed every test so far. But nowhere is it pushed harder than near a neutron star. Their compactness significantly warps space-time. When two neutron stars orbit each other, the way they spiral inward and emit gravitational waves gives us precise data on how gravity behaves in intense fields. In fact, one of the first major confirmations of gravitational wave theory came from observing a binary neutron star system, the Hall-Staler pulsar. Over time, astronomers noticed the stars slowly drawing closer, just as general relativity predicted. They were losing energy, not through light or particles, but via gravitational waves. This was indirect proof of gravitational waves long before we detected them directly. Neutron stars also help us probe the structure of matter. What happens when neutrons are compressed? What does a superfluid core look like? How resilient is nuclear matter on a stellar scale? These aren't just theoretical puzzles. Neutron stars offer observational data to answer them. Their size, mass, and spin rates help constrain the equation of state, the relationship between density and pressure. Different materials inside the star lead to different behaviors. With better measurements, we're getting closer to identifying exactly what fills their cores. Neutron stars also contribute to the universe in direct ways. Their mergers create heavy elements like gold, platinum, and uranium. While stars forge many elements, we now know that the heaviest ones likely come from neutron star collisions, and they serve practical purposes. Pulsars spin with remarkable consistency, some accurate to within billionths of a second. A network of pulsars across the galaxy could function like a galactic GPS system. Scientists have even proposed using pulsar signals to guide spacecraft in deep space, beyond the reach of Earth satellites. But one of the most exciting developments is multi-messenger astronomy, the use of different types of signals to observe the same cosmic event. Neutron stars are central to this new era. Their light, waves, and particles offer a more complete picture than any one method alone. In the era of multi-messenger astronomy, we observe the universe not just with light, but with gravitational waves, neutrinos, and other messengers. Neutron stars are ideal sources of these signals. They pulse in radio waves, shine invisible light, and ripple space-time during collisions. Through them, we connect different observations into a more complete understanding of cosmic events, and beyond their scientific value, neutron stars hold symbolic meaning. They remind us that the universe constantly reuses its material. A massive star may burn brightly for millions of years, producing elements deep in its core. When it dies, it doesn't vanish. It becomes something new, a neutron star. One day, that remnant may merge with another, releasing heavy elements across space and planting the seeds for future stars, planets, and possibly life itself. Neutron stars are more than relics of stellar death. They are links in the chain of creation. In studying them, we realize that even the smallest and most extreme cosmic objects contribute to the larger story of the universe. They're scattered throughout galaxies, quietly pulsing in the dark. And with each signal, each flare, and each collision, they reveal more about how the universe works and our place within it. Now, let's step away from data and imagine something different. Suppose you could visit a neutron star, not just observe it from afar, but drift nearby, peer at its surface, and just for a moment imagine what it might feel like to land there. Of course, doing so in reality would be instantly fatal. But this is a thought experiment. Let's imagine you're inside a perfectly protected vessel, unaffected by radiation, gravity, or the bizarre physics at play. As your ship approaches, the star appears incredibly small, just 20 kilometers across, about the size of a city. And yet it holds more mass than our sun. There's no atmosphere. No clouds, no weather systems, just a smooth metallic crust made from compressed atomic nuclei. From above, the surface might appear brushed or etched with subtle features, evidence of magnetic activity or ancient fractures. The star doesn't shine like normal stars. Most of its light is in the X-ray part of the spectrum, invisible to our eyes. Your ship's instruments convert that radiation into ghostly hues of blue and white, even at a safe distance. The neutron star's gravity exerts a powerful pull. Without your ship's advanced systems, which we'll assume exist for now, you'd be accelerating toward the surface at impossible speeds. Escape velocity here exceeds 150,000 kilometers per second, over half the speed of light. Dropping a coin from a meter above would trigger an explosion like a bomb in just a microsecond. As you drift closer, you notice something strange. The star's horizon curves upward. This is gravitational lensing. Its immense gravity bends light, letting you see more than just the visible hemisphere. A bright spot on the far side might still be visible, distorted around the edge. Your clock ticks on, but something's off. Near the star, time itself moves more slowly due to gravitational time dilation. Every hour spent in orbit equates to several back on Earth. You're not just in a different region of space. You're in a different tempo of time. Your ship holds a stable orbit. Below, the neutron star rotates. Some spin slowly once every few seconds. Others, like millisecond pulsars, rotate hundreds of times each second. If this one is fast, its surface blurs like a spinning record with beams of radiation sweeping through space like a lighthouse. The magnetic field is overwhelming. Typical neutron stars have fields trillions of times stronger than Earth's. If this one's a magnetar, its field could reach into the quadrillions. Electronics on board struggle to function. Displays flicker, alerts appear. You do your best to ignore them. Curious about what lies below, you imagine launching a probe. It dives through the upper layer, just centimeters thick, of chaotic plasma and radiation. Beneath that lies a rigid crust of dense nuclei in a sea of electrons. As it moves deeper, pressure forces electrons into protons, forming neutrons. These begin to leak from nuclei, forming a neutron-rich fluid. Deeper still lies the so-called nuclear pasta regions, where matter forms strange shapes, rods, sheets, and blobs. Beyond that is the cora superfluid of frictionless neutrons, a quantum liquid unlike anything on Earth. And at the center, possibly something even stranger, quark matter, or an exotic substance we haven't yet identified, back at the surface. It feels eerily calm. There's no sound in space, but the silence seems heavy, more a sensation of compression than emptiness. Sometimes the star glitches, a sudden spin-up caused by internal shifts. Your instruments would detect the tiniest irregularity instantly. You linger for a moment longer, taking in the strange beauty of this place. A spoonful of its matter would outweigh Mount Everest. Time itself bends under its gravity. Its interior holds matter in states we can barely imagine. Yet it simply exists, quiet, spinning, stable. Eventually you pull away. The neutron star recedes into the distance, becoming just another faint dot in space. But it continues to pulse, to speak, even as you return to familiar rhythms. You were never in danger, protected by imagination and hypothetical technology, but your perspective has shifted, because sometimes just imagining standing in a place like this is enough to make the universe feel a bit bigger and remind us that even in the quietest corners of space, all awaits. For all their bizarre traits, the gravity, the warped time, the atomic spaghetti neutron stars have captured not just the attention of scientists, but also the human imagination. Their contradictions are compelling. They are both remnants and beacons. Dead yet pulsing, tiny yet immensely powerful. In science fiction, neutron stars are often used to great effect. They're hazards, sources of radiation, or the hearts of alien engines. Writers imagine civilizations orbiting them, not organic, but mechanical or energetic, adapted to extreme conditions. Others use them as tools for time travel or strange experiments in physics. When a story needs something intense and mysterious, a neutron star fits the role. One famous fictional appearance is in Arthur C. Clarke's short story Neutron Tide, which features a ship destroyed by a neutron star leaving behind only a star-mangled spanner. The joke is simple, but it only works because readers understand just how extreme neutron stars are. But neutron stars don't belong only to fiction. They've inspired poetry, art, and philosophical reflection. Some see them as symbols of endurance, something left behind after catastrophe. Others see transformation, how destruction can give way to something new. You don't need to grasp quantum physics to feel moved by the idea of a star collapsing into a dense, spinning remnant that persists for billions of years. Neutron stars also appear in popular media, from Star Trek and Doctor Who to The Expanse and Futurama. In video games, they're often mysterious threats or dramatic landmarks, cosmic flourishes that make the universe feel deeper, older, and stranger. Let's not forget how neutron stars inspire real-world wonder. You don't need to be an astrophysicist to be amazed by the fact that a neutron star, only about 20 kilometers across, can spin hundreds of times per second and weigh more than the sun. That contrast, tiny yet massive, fast yet frozen, feels like poetry shaped by physics. People create art inspired by neutron stars. They compose music echoing the rhythms of pulsars. You'll find songs, paintings, and digital animations attempting to express the haunting beauty of these stars. And then there are real recordings, or rather, interpretations of pulsar data, radio waves from these stars converted into sound. The result is a kind of cosmic heartbeat, steady, precise, and utterly otherworldly. One of the most meaningful stories involving pulsars comes from the Voyager missions. In 1977, NASA launched Voyager 1 and Voyager 2 to explore the outer solar system. Each carried a golden record, a time capsule of Earth's culture, created in case another intelligent life form ever finds it. On that record was a diagram showing the location of Earth using pulsars. As landmarks, each pulsar was identified by its distinctive pulse rate like a signature. The idea was that any advanced civilization could decode the timing information and use it to locate Earth and determine when the spacecraft had launched. In essence, neutron stars became our return address on a message sent across the cosmos that says something about how we view these stars, not just as distant objects of research, but as part of a shared celestial map. They're reliable, constant, useful, beautiful, and just mysterious enough to keep us asking questions, even with all we've learned, the models, the observations, the theories. Neutron stars still hold secrets. We don't know exactly what's inside them. We don't fully understand how their magnetic fields change or how their interiors behave. In many ways, they remain unsolved puzzles waiting for us to get closer, listen longer, and think more deeply. And maybe that's the best kind of symbol a neutron star can offer. Not something with a simple, fixed meaning, but something that sparks curiosity. An object that spins silently in the dark, asking big questions simply by existing. Questions about endings and new beginnings, about pressure and time, about what endures when everything else fades away. A neutron star is, ultimately, a riddle written in gravity and magnetism. And like all good riddles, it doesn't need to be solved immediately. Sometimes it's enough just to know it's out there, pulsing, reminding us that the universe still holds more surprises than we can imagine. So now, we return to the question. We started with, what happens after a star explodes? We've come a long way since then. We've seen a massive star run out of fuel and collapse into something unimaginably dense. We've hovered near its powerful gravity, felt time distort, and imagined the exotic matter beneath its crust. We've watched it spin like a galactic metronome, seen it flare, glitch, and even collide. We've followed its light and gravitational echoes across the cosmos to understand what remains after the light goes out, and what remains isn't just an ending. It's a transformation, not a disappearance, but a change. Not silence, but rhythm. Not a conclusion, but a question, because even after all our research, neutron stars continue to raise fundamental mysteries. What is matter like when compressed beyond recognition? How does gravity behave at the edge of known physics? What exotic forces might lie just beneath their crusts? Are neutron stars the final stage of matter or the start of something even more unusual? At the beginning, we asked whether the universe gives us answers or just more questions wrapped in cosmic wonder. And maybe the truth is it gives us both. Neutron stars show that even destruction can lead to creation, that collapse can reveal structure, that even the dense, dark remnants of stars can carry beauty and a strange kind of peace. So tonight, whether you're relaxing on your couch, drifting off to sleep, or gazing up at the stars, remember, the universe is vast. It holds countless endings, countless beginnings, and always another question waiting to be asked. Sleep well.